Good day, worldwide university students. Welcome to the channel of Massive Quality Mathematics, where we abuse mathematics by finding solutions. As promised in the last video of vector space part 1, that in the next video, I will be doing examples of verifying some vector space axioms, considering different vector spaces like polynomials and matrices. This is the video of examples and it is titled Vector Space Part 2. Go through it until the end and I promise you will learn a lot. If you haven't yet subscribed to my YouTube channel, please press the subscription button and notification bell so that whenever I post my videos, you'll be the first one to watch. So, today, as mentioned, we're going to do examples regarding what we were doing. Remember, we proved 10 vector space axioms, and I told you that they are of great significance in the course of linear algebra. So, examples. So, let's start with number A. So, let K be inside a real number. That means it's a scalar. It's a scalar. And consider the set Pk, which is a vector space of a vector space under the operations of addition. There's an addition and there's also multiplication. You know the definition of a vector space that we talk about addition and scalar multiplication. So if you haven't watched the first part of vector space part one, you can go and still access vector space part 1. So so of addition and scalar multiplication of all polynomials of these form. So this is the polynomial of degree 4 and less. So that means this is just P4, meaning that specifically we are dealing with what to call P4. We're in P4. So we are in P4, the polynomial of degree 4 and less. So let's look at the question. They say verify the following axioms. Yeah, this is the polynomial of the form P of x equals to P0 plus P1x plus P2x squared plus P3x cubed plus P4x to the power 4, where these ones are real numbers. The coefficients are real numbers. So verify the following axioms. So closure properties. So we need closure properties because they didn't specify. You know that we have closure property under what? Under vector addition and also under scalar multiplication. You know what we are proving. That means here we'll be proving that something like P plus Q. P is a polynomial, P of x plus Q of x, which is P plus Q belongs to P4. That's what we'll be proving under vector closure property under vector addition and also closure property under scalar multiplication. We'll be proving that P also belongs to P4. So also belongs to P4. One can also say Pk. It's not a problem, but specifically we're talking about the polynomial of degree 4 and less. So the next question will be dealing with identity, additive identity and identity under scalar multiplication. We have two things with additive identity. Identity. What are we proving? We're proving that P plus 0 vector, it's P or plus 0 polynomial. So you can put this arrow. We can plus 0 polynomial is what we call is still P. So now under identity, or this is a multiplicative identity, Obvious, that's an identity under scalar multiplication. It's a multiplicative identity. It means that P1 times polynomial, 1 times that polynomial is that polynomial. So that's what we'll be proving. Also, you know, these are the 10 vector space axioms that we were dealing with, but just here we're considering what called another vector space, which is a polynomial. So also commutative property in the third Roman figure. So here we'll be proving that P plus Q is the same as Q plus P. Remember, these are polynomials of degree 4 and less. So now also the distributive property, and it is given. So what we'll be proving is that this guy is equal to K times P plus K times Q. So that's what we'll be proving. So now let's start with the Roman figure number 1. So solutions. These are solutions. So these are solutions. So let's start with the first question. Remember, we're verifying what called the closure properties. So if you let Q of X be this as given, Q of X is Q naught plus Q1X plus Q2 X squared plus Q3 X cubed plus Q. Since I told you that this Q of X belongs to P4, specifically P4. So if you let this Q of X equals to this guy, remember we're given Q of X, or we'll give P of X only. This just simply means that P of X and Q of X belongs to P4, and also their coefficients, they are real numbers. So that's what is given here. The coefficients are also real numbers. So now let's verify first the closure property under vector addition, because we've got two closure properties. So that means, and the question didn't specify which one, so we must we must do both of them, or we must verify both of them. So now we need to prove closure property under vector addition first. What are we required to prove here? We are required to prove that P plus Q belongs to PK, or specifically P4. Yeah, we can say P4, specifically P4, not necessarily P2. We can say specifically P4, specifically P4. That means we're proving that P plus Q belongs to P4. So belongs to P4. So I want to say belongs to P4. So now that's what we want to prove. So, but let's take these P plus Q. P plus Q, what is P? P is this guy as defined. P is this guy, and Q is this guy. When you define them, yeah, we define them like that. So they're in P4. So now we group the like terms. These are constant with constant. These plus these will be together. As you see, we're adding them. The P1X plus Q1X will be together. We're grouping them. We're grouping them by variable, by what called by like terms. We're grouping like terms together. Since we cannot just add everything here, we need to group the like terms. So P2 x to the power 2 and Q 2x to the power 2, we add them together. Then P3x cubed plus Q3x cubed, we also add them together. And then lastly, P4x to the power 4, then also Q4x to the power 4, then we add them together. So after doing that, we now take out the common factor of x. We take out the common factor in each these what to call monomial equation. So now we have this is constant, there's no common factor, it is still like that. But here there's a common factor of x, hence you can see. Then we just have to take out x. This is just p1 plus q1, then x outside. So here we take x squared outside, then it will appear as p2 plus q2 all times x squared. So then here we take out what we call x cube. Then we have what we call p3 plus q3 times or x cube outside. So then here we have what we call x to the power 4 is a common factor, so we take it out also. Then we have what we call p4 plus q4 x to the power 4 as a outside of the bracket as a common factor. But we know that since these guys, you know that the independent coefficients, they belongs to real number. Adding two real numbers, it is still a real number. So that means since these guys, all of them, they belong to real number. What does that mean? It means that if these guys belong to real number, this is a certain real number. So if you can just let this, maybe this guy to be A, and let this one to be B, C, D, E, we can see that we've got a simple thing like P plus Q equals to A plus BX plus CX squared plus DX cube plus EX to the power 4. This is a polynomial, you can see, of degree 3. So this thing is of degree 4. Sorry, this is a polynomial of degree 4, as you can see. So if you just let this, because this is a constant, this belongs to real number, all of them belongs to real number, all of them belongs to real number. So if you let them to be A, B, C, you can properly see, even though it's visible there above, but you can properly see what we are talking about. So this guy, it means that P plus Q, it belongs to P4. This means that. So this is a simple thing. Now that's why we have a conclusion that therefore P plus Q belongs to P, not P, K in general, but P4, since we're dealing with P4. Not PK in general, but we're dealing with P4. So now this means that P plus Q belongs to P4. So that's what we're talking about. So yeah, I hope we're done with verifying closure property under what to call yeah, let's continue. So this means that closure property under vector addition holds. So that's the other conclusion that you can give. So let's go to closure property under scalar multiplication, and you have to know what we want to prove. So we are required to prove this is a simple step, or they are called what called baby steps, so that you understand what is going on. So now otherwise this RTP is not compulsory to be written or to be shown in your workings. So now required to prove is that K times P is a polynomial, belongs to what called P4, not necessarily PK, but P4. So now this is K times P. We are starting here. It's equals to K. What is this P? P. This P. This P is these guys. So we know that this P is that guys. So now what we have to do is just to multiply by K by a scalar. We multiply by a scalar to each term inside to each term of the polynomial. So this is just K times P naught, KP naught, KP1x plus KP2x squared plus KP3x cube up to plus KP4x to the power 4. So we can group them. We can group the like terms. We can take out the variable outside of the bracket like this. We've got what called KP naught, then KP1x outside, then kp2 x squared outside, kp3 x cubed outside, and kp4 x to the p4 x to the power 4. So since these k's belongs to real number, and also the coefficients p0, p1, p2, p3, p4 also belongs to real number, so this means that k p0, k p1, k p2, k p3, k p4 also belongs to real number. So this is true. So if these guys belongs to real number, also let's say this one is a, this one is a, b, this one is a, b, c, d. You can also see that this also appear as what called sorry, let's say this one is a naught, or let me do like this. Let's say this guy is a naught, this one is a1, this one is a2, this one is a3, this one is a4. This one appears also as a polynomial like a naught plus a1 x plus a2 x squared plus a3 x cubed plus a4 x to the power 4. It's a polynomial, you can see. So that's what we're talking about, because these guys belongs to what called a real number. This will mean that k, therefore k to the k times p also belongs to what we call p4. So therefore the closure property under scalar multiplication holds. So that's what simply what we are talking about. So now let's go to the next question. That was verifying the additive identity and the multiplicative identity. That's an additive identity under vector addition, or under VA. So now what we were required to prove is that polynomial plus any polynomial plus zero polynomial is that polynomial. So we take p as we assume that p is our polynomial of degree 4 or less. So this is p plus 0 equals to p. So now we just need to prove the left hand side until we get what called the right hand side, if possible. So then this is what called p plus 0. We know that p is this polynomial, and 0 is just a zero polynomial. You know that it has got what called zero coefficients. It has a zero coefficients. So now so this is very simple. What we have to do is just to add what called the corresponding like terms. So this is what we call p0 plus this one plus 0, which is this one. Then as what we were doing there, we're just adding this and this and this and this and that. So that's what we are doing. It's a very simple thing. So now that's what we have here. So therefore we need to take out the common factor as usual. So these will remain the same, and this taking out, and this taking out x squared, this one taking out x cubed, this one taking out x to the power 4. You can even see here we're taking out this x to the power 4, we're taking out this x cubed, we're taking out this x squared, we're taking out x, here we're taking out nothing. So it remains like that. There's no common factor. But we know that p0 plus 0 is still p0, then p1 plus 0 is still p1, then p2 plus 0 is still p2, and p3 plus 0 is still p3, and p4 plus 0 is still p4. So this, if you can see, it's a polynomial. It's an expression for the polynomial p. So this thing is just equals to p, and this means that this is equals to the right hand side. So that's what where we wanted to reach. So therefore this means the additive or identity property holds. It holds. So That's how simple it is. So now let's go to the identity or multiplicative identity. We can add what we call multiplicative. So it's a multiplicative identity under scalar multiplication. So we're required to prove, as I told you, this is a baby. These are baby steps. So now this is just 1 times p equals to what we call 1 times p equals to p. So now we need to prove what we call the left hand side, which is this guy. So this is just 1 times what is p. You know that it is given by that expression based on the definition of polynomial. So then we multiply by 1 to each coefficient of the polynomial expression. So this is 1 times p naught, which is this one, 1 times p1, 1 times p2, 1 times p3x cubed, 1 times p4x to the power 4. We're just multiplying. So then when you multiply the coefficients together, 1 times p naught, we get these, 1 times p1, we get p1, 1 times p2, we get something like this. So this guy, as you can see, it is still an expression for what? For p. So this is just equals to what? Right hand side. Therefore, the identity under multiplicative identity under scalar multiplication holds. So that's what it's all about. So now let's look at Roman figure number 3, where we're proving the commutative property. So we're required to prove that p plus q is equals to q plus p. So that's what we're required to prove. So what is p? So p, it's p naught plus p1x is this guy, plus p3x cubed plus p4x to the power 4, and q is like this. Also we know that because we've defined this. So now we add what we call the like terms, this one with this guy, that one with this one, this one with this one, this one with this one, this one with this one. So that's what is happening here. We're adding them. So now after doing that, so we take out the common, we take out what we call the common factor. Here there's no common factor. Here there's common factor of x, we take it out. Here there's common factor of x squared, we take it out. Here there's a common factor of x cubed, we take it out. Here there's common factor of x to the power 4, and we also take it out. So now after doing that, we know that these guys are what we call, they belongs to what we call real number. So they belong to real number. So since they belong to real number, so what does this mean? Since they belong to real number, to this guy, it means that we can commutate inside. Instead of saying p naught plus q naught, real numbers are commutative. So we can commutate. So this one is just q naught plus p naught. We're allowed q1 plus p1 because they are real numbers. q2 plus p2. q3 plus p3 from p3 plus q3. q4 plus p4, we can commutate these real numbers. So then after commutating, we expand again. So we know that this is q naught, this is just plus p naught. When multiplied by x, this is q1 x p1x plus q2 x squared p2 x squared q3 x cubed p3 x cubed q4x to the power 4 and p4x to the power 4. We just multiply by those what call s squared, s cubed, and x to the power. We remove the brackets. So then after we group what call the same, or what call letters. This is just what call q naught, q1x is there, q naught. Let me do this. This is just this q naught, q1x, q2x squared, q3x cubed, and q4x to the power 4, which is this guy. So then the remaining thing the remaining thing is for this guy, so which is p naught plus p1x plus p2x squared plus p3x cubed plus p4x to the power 4. And this is just, what is this guy? This is just q plus, this is just what called p. This is equals to what called the right hand side. Therefore the commutative property do what? Holds. So that's how simple we're doing this thing. This is the very same thing that we're doing when we're proving those 10 vector space axioms, and this is also the very same thing that we have to also apply here. So I hope this is very clear. Let's move to the Roman figure number 4, which is the last question. So now here we're required to prove this is the distributive property. So here we're required to prove that k times p plus q is equals to these are kp times k. We're just distributing the scalar. So now let's prove this left hand side. Left hand side. So this is k into p plus q. Where there is p and q, we're putting those things. Polynomials is these plus this. So this is visible. So now then this is k. We're adding as usual the what called the like terms. Simple thing. We add what is inside the bracket first. So then we multiply by scalar. That's when we're multiplying by scalar. This one multiply by these multiply by this, that multiply by that scalar, by that scalar, by that scalar. This is k times this, k times this, k times this, k times this, k times this. So after doing that, then we now have to distribute k. In this we need to distribute k, 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 in this we need to distribute k. So now this is simple as k times p naught, which is kp naught plus kq naught plus kp1x, kq1x, kp2x squared, q2x squared, kp3x cube, kq3x cube, kp4x to the power 4, and kq4x to the power 4. So after then we need to group the like terms, which is what call these together, kp naught together, kp1 together, kp2x squared together, kp3x to the power 3 together, then kp4x to the power 4 together, which is this guy. So now then, which is that guy. So then we take the remaining thing for q, which is kq naught, kq1x plus kq2x squared plus kq3x cubed plus kq4x to the power 4. So then we know we can take out the common factor here of k, and also we can take out the common factor there of k. So when you take out the common factor here of k, so this is just k into p naught plus p1x plus p2x squared plus p3x cubed plus p4x to the power 4. And here when you take out the common factor of k, then we have what called q naught plus q1x plus q2x squared plus q3x cubed plus q4x to the power 4. Then what is this guy? But what is this? This guy is what? It's p. It's a polynomial p. This is k times p. Then what is this guy? But that guy is q. So now this is just k p times k q, and this is the same as right hand side, what we are required to prove. This means that the distributive property holds. Distributive property holds. Therefore, distributive property holds. I think this one is clear. Now we're about to go to the next example, which is number B, which is now in terms of matrices. Number B. So we need to go to number B, which is this one, the second example. So number B, let let the M33 be the set of all 3 by 3 matrices. You know, this is what called a square matrices. That's a square matrices, be 3 by 3 square matrix. So let M33 be the set of all 3 by 3 square matrices with trace equal to 0. Do you know what is trace? The trace is the sum of diagonal elements. That means the sum of diagonal elements is equals to 0. For example, if we take a matrix A, B, C, D, this is M22. It's not related to this. I'm just giving an example of explaining what is trace. So a trace of A is A plus D. So they're saying that this is 0. So they're saying that this is equals to 0. So that's what the question is saying. That's what the question is saying. So now, that's the diagonal elements. So yeah, that's the thing. If you let this one be a 3 by 3 square matrices with trace equal to 0, which I just explained a few minutes ago, that is this. Now they are kind of like describing the set or the vector space that we're dealing with. That is M33. It's A equals to something like A11. This is a 3 by 3 matrix, as you can see, and the trace, which is the summation of this, the sum of these diagonal elements, it equals to 0. So this is Aij belongs to real number. That means we're just saying that we're just generalizing that these diagonals, these entries, sorry, the matrix entries, they belongs to real number. That's what this means. So trying to play around I and J. So you can see that if you say this is 1, this is 1 1, then it's A11 belongs to real number, A12. You can just play around that. So that's simple. So that is this be a vector space. That's a vector space under the same operations of vector addition and scalar multiplication. So that's addition and scalar multiplication. So that means we're just talking about another vector space V, which is just in this case, you know, when you talk about our definition, is what you call addition and multiplication with M33. Now specifically we're dealing with what you call these 3 by 3 square matrix, 3 by 3 square matrices. So verify the following axioms for all A, B, C belonging to M33, which is 3 by 3 square matrix. So remember, the matrices are represented by capital letters, and the entries can be small letters or can be what called real numbers. So and K belongs to real number. Remember, even the entries, it belongs to real number. So we need to verify the following axioms for A, B, C belonging to M33 and K belonging to, this is a scalar. This one are vectors. They're like a vectors. So vectors in the form of matrices, that's the thing. So but we're dealing with matrices. So now you verify these for A, B, C belonging to M33 and K belongs to real number. The closure properties, that's the always two things that we have to talk about. Also we need to talk about what called vector addition, since they didn't specify vector addition, and that is scalar also multiplication. So that's proving that A plus B, two matrices, belongs to M3, 3. So that's proving that KA belongs to M3, 3. So now we also have got what we call closure property. What we're proving is that A plus B is the same as B plus A. So we're proving that A plus B is equals to B plus A. That's a commutative property. So we also have got what called additive identity and identity under scalar multiplication. That is additive identity under vector addition. Is that matrix A plus 0 matrix is a matrix A. So now we have got what called the multiplicative identity. That is 1 times matrix A. That is a 1. It's a what called, it's just like we can say it's a matrix of 1, or we can say it's a what called just 1 is a scalar. 1 is a scalar. So this is just equals to 1 times A is just what called also a matrix A. So now we also have to prove the distributive property. We know what we're proving here is that this is just a K times A plus K times a matrix B. So that's what we are talking about. We're definitely talking about. So now let's go on. Solutions. Let's present our solutions. So now we need to let B another matrix called B, because we know that in the last Roman figure number 4 we have what called, and even in the commutative A plus B. So we need to have a matrix B to construct matrix B also. So this is a matrix B belonging to M33, is a square matrix with these entries B11, B12, B13, B21, B22, B23, B31, B32, and B33 belongs to these M33, such that the trace of B, obvious, this is the property of a set, is it also need to be satisfied. This property must be satisfied. This property must be satisfied. In fact, we are saying it must be proven to be true. So that's what we're talking. It must be proven to be true. So if we let this be a matrix, depending on the vector space, on the vector space, there is a property that the trace is 0. So that means the sum of these diagonal elements is equals to 0. So now let's go to the first Roman figure, which are verifying closure properties. So closure properties. So we told you these are baby steps method required to prove, and just decide not to write it or decide to write it. It's your own choice. So now we have what called the closure property under vector addition first, which we are proving that a matrix A plus matrix B belongs to M33. So to a 3 by 3 square matrix. So now we have this matrix A, which is this guy, and we have this matrix B, which is this guy. So we know that when we are adding two matrices of the same sizes, just we add, when it comes to the addition of matrices, we add matrices of the same sizes. This is a very important property, or this is a very important property. Adding two matrices, we add matrices of the same sizes. So that's what happened. That will be square matrices. So now we were adding this and this. We add what we call the corresponding entries. So that's also another property. So we add what we call the corresponding entries. That is this one plus this one, this one plus this one plus this one. We add what called the corresponding entries. That's why we have got what called a11 plus b11, a12 plus b12, a13 plus b13, like that, and like that. So that's what we have here. So after adding, we know that since aij and bij belongs to real number, we just want to generalize everything that is inside here. Instead, you can say these, and just mention them like that. Belongs to real number if you want, but just to minimize a lot of information. So we just have to say since aij plus bij belongs to real number for this, then what does that mean? It means the whole matrix, these components inside belongs to real number. It means that this is a 3 by 3 is a 3 by 3 square matrix, because this is a constant, 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 this is constant, this is a constant. So this means that this guy belongs to what? To M33. And if it belongs to M33, that's what we wanted. So therefore, we need to go to the trace. Now, we are not done. We need to prove that the trace is 0. Remember, according to the set that we are given, there's another condition that we are supposed to show, that the trace is also the sum of the diagonal elements is 0. So the trace of a plus b is just these diagonal elements. We're adding these diagonal elements, which are just a11 plus b11, a2 plus a22 plus b22 plus a33 plus b33. That's what we're adding: a11 plus b11, a22 plus b22, a33 plus b33. So now we group what we call the a's together. So this is a11 plus a22 plus a33, and the b's together, which is what called b11 plus b22 plus b33. So, but what is this guy? What is this guy? According to the definition, this is 0. This is a trace of A, and this is also the trace of B. And we know that the trace of A, according to the definition, is 0, and the trace of B, according to our assumption, is 0, based on the set. And this is 0 plus 0, which is just 0. So then, therefore, because the condition is also satisfied, everything in the set is satisfied, therefore you can conclude that therefore A plus B all belongs to what called M33. You don't conclude before you prove this condition. Don't conclude that something belongs to the set without first verifying all conditions inside the set. It's very important. This is very important. So now, therefore, that means the closure property holds under vector addition. So let's look at the closure property under scalar multiplication. What are we required to prove? We're required to prove that K times A belongs to M33, so which is a 3 by 3 square matrix. So we're just multiplying these by a scalar. This is just K. What is A? A is this matrix, remember? So now when you multiply a scalar by a matrix, or multiply a matrix by a scalar, we multiply each entry of the matrix by that scalar. So that's what we are doing. So this is just a k times this entry, all entry, we're multiplying it by k. So that's why we have got ka11, ka12, ka13, ka21, ka22, ka23, ka31, ka32, ka33. So like that. So you know that k belongs to real number. It is defined in the definition. Also, aij belongs to real number for I, j being 1, 2, 3. So now, what does this mean? This means that also k times aij, this is a real number, this is a real number, this is a real number, real number, real number, real number, real number, real number, real number. So this means that k aij also belongs to real number for I, j equals to 1, 2, 3. So since these entries inside belongs to real number, that means the whole thing is belongs to a 3 by 3 square matrix. So that means the whole matrix is a 3 by 3 square matrix. So that means this guy belongs to what called M33. So we need to verify the trace also. The trace of Ka, so it's the sum of the diagonal elements. We need to verify that is 0. So which is Ka11 plus Ka22 plus Ka33. So we can see that here we can take out what called K outside, and inside we are left with A11 plus A22 plus A33. So this is just what called A. What is this? It's A. It's A, but not necessarily A, but this can be a trace of A. Not A, but trace of A. Sorry, that's a typing error. The trace of A, this thing. But what is the trace of A? Trace of A is 0. So then K times 0 is 0. So therefore we can conclude that Ka belongs to M33, and the closure property under scalar multiplication holds. So that's how simple we're doing this thing. So remain figure number 2, commutative property. So what are we required to prove here? We're required to prove that A plus B is equals to B plus A. A plus B is equals to B plus A. Those are matrices. So let's prove the left hand side until we get what called the right hand side if possible. So we know what is a matrix A, and we also know what is a matrix B. So we are adding what we call the corresponding entries. So that is just what called this matrix plus this matrix. It means we are adding what we call the corresponding entries. This one and this one, A11 plus B11, A12 plus B12, which is this, A13 plus B13, which is this. Like that, adding what we call the corresponding entries, A21 plus B21, A22 plus B22, which is this, A23 plus B23, which is this, and then you add until the last row. So now, after then we have that. So then this means that since this combination belongs to real number for I and J equals to 1, 2, 3, so it means that we can be able to commutate real numbers. 2 plus 3 is the same as 3 plus 2, you know that. But if they're saying these guys belongs to real numbers because it's one of the real numbers, so now even square root of 5, even if we say square root of 5 plus negative 3 is the same as negative 3 plus square root of 5. So that's what we're talking about. So now, because they are real numbers, then we can commutate. We can write it, this one is like this, B11 plus A11, B12 plus A12, B13 plus A13, B21 plus A21, B22 plus A22, B23 plus A23, B31 plus A31, B32 plus A32, B33 plus A33. So that's what we're talking about. Then you know that we are adding. Then we can separate these two matrices to show that we're adding two matrices. We're adding this matrix with this matrix. This is from here. We just separate again. So then we have this. But what is this? This is matrix B. What is this? This is matrix A. And this is what we wanted. This is the word called right-hand side. Right-hand side. Therefore, the commutative property holds because that's equals to right-hand side. So that's simple. Let's go to the next thing. We need to prove trace now. That's equals to right-hand side. We need to prove trace before we conclude. We prove trace before we conclude. It's very important. What are we before we conclude? What? Before we conclude that B. No, not before we conclude the closure property. So now, this thing, trace of A plus B equals to 0. This is proved above. We know. We don't have problem. We've proven this above. When we're dealing with what to call closure property under a vector addition, that means we're left with proving the trace of B plus A, which is adding the diagonal elements of B plus A. What is B plus A? You know that B plus A is this guy. It's here. Is this guy. Is this one. So now we're just adding these diagonal elements, which is B11 plus A11, B22 plus A22, B33 plus A33. So now that's what we're doing. The trace of B plus A will be B11 plus A11 plus B22 plus A22 plus B33 plus A33. So when we group them, we have what called those ones for A's together, A11 plus A22 plus A33 and B11 plus B22 plus B33. We know that this is just a trace of A, this is just a trace of B, which is just equals to the trace of A is 0, the trace of B is 0. That means the trace of A plus trace of B is 0. So this means that trace of A plus B is equals to trace of B plus A is equals to 0. That means the commutative property holds after proving this condition. So that's what we are talking about. So let's go to Roman figure number 3. Additive identities. Additive identity under scalar and under vector addition. And what to call the multiplicative identity under scalar multiplication, or SM. So that's what we're about to prove. So now we have what we're required to prove is that a matrix A plus a zero matrix is equals to A. A zero matrix is a matrix like this. If we talk about it belongs to what we call M33. If this belongs to M33, a zero matrix is a matrix like this: 0, 0, 0, 0, 0, 0, and 0, 0, 0. It has got what called 0 entries. So 0 entries. Remember, 0 vectors has got 0 components. So this is so important. What does this mean? This means that vectors, in vectors we talk about components, in matrices we talk about entries, and in polynomials we talk about coefficients. So that's very important. So now this is what we are required to prove. So then we can prove what called the left hand side, which is just, if you do this, then we just need to remove this. But if it just equals to, then we can just do equals to. That's a typing error, human being error. So prove the left hand side. So this is just A plus 0, which is equals to, what is matrix A? Matrix A is this guy. Then what is matrix B? Then matrix 0 is this guy, 0 matrix, sorry. Now this is matrix A, this is 0 matrix. We're adding them together. We know that we add the corresponding word entries, this one plus this one, this one plus this one, this one plus this one. That's what we're having here. we're adding what's called the corresponding entries. This one plus this one, this one plus this one, this one plus this one, this one plus this one. Corresponding entries in each row. Then we get these result. We get these results. So then we now have what called a11 plus 0 is just a11. a12 plus 0 is just a12. a13 plus 0 is just a13. Then a21 plus 0 is just a21. Then a22 plus 0 is just a2. a23 plus 0 is just a23. Like that. So we know that this guy is a matrix A. That guy is a matrix A. So that means this is equals the right hand side. We proved, but we also need to prove the trace. We don't end there. We don't end there. We need to also show another property, which is the trace. Then the trace of A is 0. This is given. That's what we know. That means it's the right hand side. The trace of A is 0. We need to prove that the traces are equal, obvious. But the trace of A plus 0 is just adding the diagonal elements of a matrix A plus 0 matrix. So which is this? We're adding these diagonal elements. We're adding these diagonal elements, which is a11 plus 0, a22 plus 0, and a33 plus 0. So we're adding those diagonal elements. So now that means we're talking about a11 plus 0, a22 plus 0, a33 plus 0. But 0 plus 0 plus 0 remains as 0. This is just a11 plus 0, which is just a11, a22 plus 0, a22, a33 plus 0 is still a33. But this one, it's a trace of what? It's a trace of A also, which is just 0. You can just say this one is a trace of A. So which is 0. So now this means that the trace of A plus 0 is equals to the trace of A is equals to 0. And that's what we're supposed to prove also. So then this means that this is proven. A plus 0 is equals to A. That's a additive identity property under vector addition. Let's look at the additive identity under a scalar multiplication. So we need to prove that 1 times A is just A. How can we prove this? 1 is a scalar. So a 1. So if we, so that's left hand side is equals to this. This is equals to 1 times what is a matrix A is this guy. So when we multiply each entry inside by a scalar. So this is just like this. It's visible. So now 1 times A1 1 times A1 2 like that. So then what is 1 times A1 1 is still A1 1, A1 2, A1 3, A2 1. This is the result of this. So now what is this matrix? This matrix is A. It's still A. That's a matrix A, you know, this one. It's a matrix A, and this equals to the right hand side. We have proven that, but we need to show also the trace. We need to prove that the trace of 1 times A is equals to the trace of A is equals to 0. That's what we need to show. That's what we need to show. But what is a trace of A? It's given, it's 0. It's given as the definition. So then what is a trace of 1 times A? We're just adding what we call these diagonal elements. So this will be what we call, no, not these diagonal elements, not these ones, but these diagonal elements of 1 times these diagonal elements. So now that's what we have here. It's 1 times A11 plus 1 times A22 plus 1 times A33. So this still the same. 1 times A11 is still A11, A22 plus A33. And this is just a trace of what? Of A, which is 0. So therefore, this means that the trace of 1 times a matrix A equals to the trace of matrix A, it's equals to 0. So thus we prove the condition in the set. So that's the thing. So we can go to remaining figure number 4, the last problem of our examples. So here we're required to prove the distributive property. It's an obvious case. It's very long but very simple, not that complicated. So now we're required to prove that k into a plus b is equals to k a plus kb. We just distribute this color each to get this to each matrix. So now we need to prove what called the left hand side, which is just equals to this, but this is equals to what is a matrix A is this guy, what is matrix B is this guy. So that's k into this. We first start by following the Bodmer's rule. That's a basic principle in mathematics. From primary education, we learn about the Bodmer's. We start solving what is inside brackets. So that is easy mathematics. It's just a principle that everyone is to follow in order to get correct calculations. So now we need to add these two matrices. So we know when we add matrices of the same sizes and we add the corresponding entries. So that's what we do. So that's adding A11 with B11. So we add them together like A11 plus B11, A12 plus B12. So then A13 plus B13 like that up until we get this guy. And you can remove this out bracket. It's insignificant now because we already have one bracket. It's enough. So it's just a typing error. You can just remove that, this bracket, these brackets. So now then we have what called k times this. We know that if we are multiplying matrix by a scalar, we multiply each entry in so we need to multiply each entry, this guy, k multiply with these, k multiply with these, k multiply with these, k multiply with this, k multiply with these, k multiply with these, k multiply with these, k multiply with these, k multiply with these. So now that's what we are doing. So that's k multiply with this entry, 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 and k multiply with this entry. So then after multiplying with those entries, we now need to multiply to remove brackets. We need to consider each monomial expression and now remove brackets by distributing k to each entry. So that's k times a11, which is ka11, plus k times b11, which is just plus kb11. Also to this entry, also same applies to this entry, same applies to that entries, up until you get something like this. So now after doing that, we know that we can separate again, like the ones with a's together. We know that we're adding matrices. This is the same as adding this and this. You can see this is the same as adding this and this. So what does that mean? It means that here it's visible. You can remove this outer brackets. It's insignificant, as I told you. So you can't have two brackets. So now we have what called, we can take out k as a common factor. So we have k outside, and we take out k, we're left with a11, a12, a13 like that. So also here, if you take out k, you're left with b11, b12, b13 like that. So now, but what is this guy? This guy is just a. What is this guy? Is just a matrix B. So we're talking about ka plus KB, and this is just a right hand side. We've proven, but we're not done because we need to prove that other condition. So we need to prove that other condition. So this is the condition that we need to show, the trace one. We need to show the trace of KA plus B and the trace of that. So the trace of K into A plus B is just equals to, we can take out K, we can just, because K is a constant, we can just have the trace of A plus B, but we know this trace of A plus B is 0. This is just a K into 0. We've proven it above. So this is just K times 0, which is just 0. Since the trace of A plus B is 0, this is proved above or proven above. Also, you can just have proved above or proven above. So that's the same thing. So now, we also now have to prove the trace of KA plus KB. But we know that here, we can take out the common factor of K. This is to be the TR into K into A plus B. So, but we know the trace of A plus B, it's 0. This is just K times 0, which is just 0. Therefore, the trace of K into A plus B, it's equals to trace of KA plus KB, it's equals to 0. And we've proven the condition. So this marks the end of this solution of the end of the presentation of the solution of example number B, which we were dealing with matrices. So now in the next video, we've finished about 10 vector space axioms. We took some examples. So if you have any question regarding this or any thing regarding linear algebra course or the course of linear algebra, you can ask your question by writing it in the comment section, and I will consider it and respond in due time as I promised. So now in the next video, I will be talking about what to call subspaces. So now we'll be starting what to call a new subtopic called subspaces. It is still a subtopic under vector spaces. So we need now to talk about our vector spaces, subspaces, that a vector space can be contained within another vector space. So it's possible, and we'll be talking about what happens and how do we prove that a vector space is a subspace of another vector space. So now, if you find this video very interesting and opening your mind, and you are learning a lot, you are learning something about linear algebra, you can support me by sharing, liking, and subscribing. Press the subscription button if you haven't subscribed, share, like, and also press what called the notification bell, so that whenever I post my videos, you'll be the first one to get notified and to watch them. So yeah, thank you very much for your time. Thank you very much for listening to me. Thank you very much for everything, and thank you very much for your support in advance. So thank you very much.